I invite Professor Amit Apte to introduce the speaker.
Okay, welcome everyone, and it's a pleasure to introduce Paulo Silva, whom I have never met before, and as we were just chatting, it's difficult to introduce that I have never met. In a normal conference, I would have met him before, but because of course, the pandemic, that's not possible. But thanks a lot for agreeing to give the talk in the virtual mode. So Paulo did his PhD in applied mathematics at University of Sao Paulo, if I am not mistaken. And his main research interests are in optimization, complex and nonlinear optimization. And today he's going to talk about using optimization for intervention against COVID-19 robot dance. So looking forward to it.
So thank you very much for the introduction. Can you hear me? Just to make sure, can you hear me?
Yes, we can hear you.
Okay, good. So I would like to thank the organizers for inviting me to give this talk. I'm very honored for this opportunity to represent Brazil in this very nice conference. It's a really pity that I cannot be there. I would really like to go to India for the first time. I was looking forward for it, but unfortunately, it was not possible in this time. So probably next conference, next time. Okay. It's interesting because I'm going to talk about something that I did not plan at all when I got the first invitation to give a talk in this conference. I was going to talk about some robust support vector machines. But then the pandemic came, the conference was postponed, and I decided to change very drastically the topic of my research to join the effort to understand how to use mathematics to help with the control and the understanding of the pandemic. So this is a joint work with many colleagues. I will try to give the names during the talk. And what I'm trying to present to you is how to use optimization to help design intervention measures against COVID-19 in a complex network. Okay, so here we go. So in order to do so, I need to introduce to you, I don't know how many of you are aware of the idea of compartmental models, the mathematical epidemiology models that we use to predict how a disease is going to spread through a population. And actually, those were very important just in the beginning of the pandemic. Some people from the UK, from Imperial College, they made some simulations that showed that if the government did not take strong measures to slow down the spread of COVID-19 due to the characteristics of the disease, because it spreads very fast, and also because the whole population was susceptible to it. The number of people that would get sick and therefore they would need special health treatment would be so high that it would overwhelm the health systems in many countries, and that would be a disaster. And once that was reasonably well understood, the governments took action, and many of them started declaring things like lockdowns and other non-pharmacological measures to slow down the spread of the disease. So this is a very important, at least from my point of view, and I believe from everyone's point of view, a very important application of mathematics in real world, in a real world emergency problem. So that was very important. And what we're trying to do here is to build upon that idea. And instead of just doing simulations, we want to do also optimization. Okay. So to do so, let me introduce you to those of you that don't actually know something about compartmental models. So those are very simple models that try to capture the dynamics of infectious disease. And the idea is to group the population in different groups that we call compartments, according to the stage of the person in the disease. And the dynamics, how the disease evolves, is given by the rate of movement from people from one of those compartments to another compartment. So they're moving along the different stages of the disease. And we say the two compartments, they interact if the input or the output of one of those compartments depend on the other, okay? Just to give a better idea, let us see the most simple and most famous compartmental model, which is the SAR model. I will call it SAR or SIR. SIR is better. Then you divide the population in three groups: the susceptible, the infectious, and the recovered group. So people that are susceptible are people that they can get sick because they don't have a strong immune response to the disease yet. The people that are infectious are the people that are actually actively spreading the disease at that moment in time. Okay, so they are sick, but not only they are sick, they are able to transmit the disease to other people. And the people that are recovered are people that are not infectious anymore. So they might even still be sick, but they're in another moment of the disease where they don't transmit as much. For example, they went to the hospital, or for example, they went, they got well, that's very good. Or even if they pass away, they will move to the recovery compartment. We don't have a separate compartment that call it the deceased or something like that. It's not that important for this simulation, okay? And what you usually have is the rate of movement from one compartment to the other. So, for example, here you see that for going from susceptible to infectious, you have to get sick, you have to get the disease. So you have here the people that are infectious, we call it, we use the I variable for them, susceptible the S variable, and recover the R variable, okay? So if you are susceptible, there's the chance that you can get infected is proportional to the amount of infectious people in the population. So this is I divided by N, where N is the total amount of people in the population. This is the proportion of sick people in the population. And the more people susceptible, the more people will get sick. So if you are in a population where everyone is susceptible, which was the case for COVID-19, it's very easy for people to get sick because basically everyone can get sick if they find one of those infected people. And there is also this special parameter here, this beta parameter, that tries to convey information about the disease and the behavior of the population. So if the disease is can spread very easily, is very contagious, then beta will be big. If the region is very urban, very populated dense, many people in the same place, the beta will be big. And if it's not if people are very spread around so they don't meet much, beta will be small and things like that, okay? And you also have this gamma parameter that tries to capture things like how hard or how easy is for you to get from infectious to recovered. So if the disease is easy, is not a very serious disease, and you get well fast, then gamma will be big. Otherwise, if the disease is usually lasts a long time period and you stay infectious for a long time, then gamma will be small and things like that, okay? So if you do some assumptions on how the disease spreads and how you recover from the disease, that leads you to an ordinary differential equation that you have to solve. And the solution of this ordinary differential equation, which is present how the number of susceptible, infectious, and recover will evolve in time. So that will give you curves that show the number in each of the compartments evolving in time, okay? Just to make a little change of notation, because usually I prefer to talk about other parameters. If you define the parameter R naught as beta divided by gamma. This is well known and it was widely used during the COVID-19 spread. It's called the basal reproducible number, and it's basically trying to convey the number of people that a sick person is expected to infect during his disease period, okay? So if R naught is bigger than 1, then one sick person is spreading the disease to more than one person, and this will lead to some kind of exponential growth of the number of sick people up to a certain moment where the number of susceptible is so low that it compensates for the big R naught, okay? And if you call T infectious, the time of infectious, which is the mean time that you stay spreading the disease. So if this number is like 3, it says that for 3 days, for example, is the time window where people see that an infected person will infect the most, okay? If you have these 2 parameters, you can rewrite that equation in this way, which it's, at least for me, is more reasonable to see. So you have this R naught parameter, which is big if the disease spreads very fast, and it's divided by the time that you have to do that spread. So if you spread 2 people during the whole period where you are sick, but you stay sick for 5 days, then it's 2 divided by 5 the number of people that you would infect in a single day. Also, we divide the total number of people by the population in such a way that the variables now, they represent proportions of the population, not the absolute number, but the proportion. So like if S is 0.5, you're saying that 50% of the population is susceptible. And if the I is 0.2, that would be really big, that you're saying that 20% of the population is spreading the disease at this right moment, and so on. Okay, so we normalize the number of people such that they add up to 1, and it's easier because with this you don't have to care too much about absolute numbers. Like if you're doing your model in a population that have a few million people, it's the same that if you're doing your model in a population that have 1 billion people. Okay. Okay, and what is good about compartmental models? What is very nice about them is that once you get the grips of it, once you understand it, you'll see that it's very easy to adapt it to convey other situations, different situations. For example, very natural adoption of the SAR model, that it was actually the most used during the COVID-19 outbreak, is this extra model where you have another compartment between the infectious and the susceptible, which we call the exposed compartment. And those are people that are already sick, so they got the disease, but they're not sick enough to spread the disease. So the virus load is building up in their bodies, up to a point where they start spreading the disease actively, and then they will move to the infectious compartment, okay? And in the case of the COVID-19, taking into account this exposure period was important to understand the dynamics of the disease, okay? So it was good and it was a nice idea to add this extra compartment to the model, okay? And now what you have is that you have a mean time that you stay exposed. So we call it T-inc for time of incubation. We are incubating the disease, and you have a mean time that you stay exposed, okay? And once again, you arrive in a simple ordinary differential equation, which is reasonably easy to solve. You actually have a kind of a closed solution, but you don't have a really good closed solution for that. So you have to solve it numerically, but it's a very easy to solve, very nice, very stable. Basically, any method that you throw it will give a reasonable solution, unless you use Euler method. If you use any kind of second order method on, you get a reasonably nice solution for this problem, okay? Okay, so up to this point, we are in the situation of the Imperial College. We have the model. We have to come up with the constants, which are basically the R naught, the reproduction number, and the time of infectious and the time of incubation, okay? And if you have those, and you have an estimate of the number of people that are susceptible, exposed, infected, and recovered in your population, you can run your model, do a simulation, and predict under those circumstances how the spread of the disease will take place, okay? Good. So once they did that, they said, okay, this is going to be a major disaster. We cannot allow it to happen. So if you look at the model, you start thinking about it, and what is the parameters that you can try to control, that can try to change in some way? And this is basically this R naught parameter here, because the R naught parameter, it's in a single parameter, it's in a single number, it conveys many different aspects of the disease. For example, if the virus transmits very easily, R naught is going to be big. But as I said, if you are in a city densely populated, R naught will be big. But if you are in a rural area, which is very lightly populated, R naught will be much smaller. If you start a lockdown and people just stay home, even though they are in a big city, R naught will decrease. If you make people wear masks so that it's harder for the virus load to go to the environment, R naught will decrease too. So this R naught parameter is a special parameter that you can actually fine-tune, you can actually control in some sense by changing the behavior of the population. You cannot change the virus, that's true, but you can change the behavior of the population. And that was what we had, because if we could change the behavior of the virus, then we would need a medicine or something like that, or a vaccine. But we didn't have that in the beginning of the last year. The only thing that we could actually control is how people would behave. So in some sense, this R naught variable here is some kind of a control variable that you can try to modulate, you can try to control, to select in such a way that you change the dynamics of the disease, for example, to make the number of sick people low enough so that your health system can cope with it, can treat the people, okay? So very good. So what we try to do, we try to write some kind of model that would accept that we can control R naught to achieve specific goals. And we wanted to write the software that will show to the decision makers which are the R naught that they would need to achieve certain goals. And just to make things a little bit more fun, we don't live in a single population environment, actually. We actually live in a big state here, in the state of Brazil, and in a big country, which is Brazil. And in this state, we have São Paulo City, which is a major international hub, and the biggest city in the country, and the biggest city in the state. But you will see that from everywhere in the state, people come to São Paulo and go from São Paulo to other places. But we have also local hubs where people commute every single day so that they spread the disease geographically. So the disease will probably get into the country through São Paulo airport, okay, and Rio airport, which is nearby, is like here, okay, and then people would come from Campinas, which is the city where I live, go to São Paulo to work during the day, something I did for many years in my life, and they would come back at night sick because they got sick in São Paulo, and they would spread the disease at night, and then Campinas would have sick people, and then people would come from another city here nearby, I don't know, São Carlos, and they would come to Campinas to work during the day or to do some business during the day, and they would go back at night and they would spread the disease. And so we wanted to write a model that would be able to capture this dynamics of multiple populations that interconnect, and where the disease is in different stages of its population. So, for example, it's expected that the disease would spread faster in São Paulo and is lower in the countryside, in the interior of the state. And it would, I don't know, have a peak here in São Paulo, and that peak would only arrive at Ribeirão Preto some months later. So we wanted to capture that information a little bit. So how you do that? You create many different compartmental models, one for each region in some sense, or one for each of those hubs that would represent a region in the country or a region in the state. In our case, we're thinking about the state. So, and we focus in what we considered was the most important dynamics, which is there are many people that work during the day in the main cities, in the big cities, and they go back to their smaller cities during the night and during the weekend. So what we had would be a dynamic that would change during the night. It would be the usual model with separate regions, but during the day, the dynamics of the susceptible people from a city or from a region I would go to another region, okay, and they could get sick. So we had to split up all the variables with two indices, so such that things like Sij would mean the fraction of the population of city I that live to work during the day or live to do business in the city J, and they come back during the night, taking the disease with them, okay? And we would need to modify the differential equation to take that into account. So basically what you have, you now have many subvariables that would try to say how people are moving from one region to the other. So you have two indices, and you would need to be careful how those things interconnect. And you also need the information of how many, what is the fraction for every single city or for every single region that go to work during the day in another city, at least in the mean of that, some kind of statistical information. We actually had that because, fortunately, one of our co-authors, he was working with that kind of data ready before the pandemic, and he had access of a very large database of cell phone movements from different telecommunication providers in Brazil. It was a very rich database. It's very hard to work with it because everything is very private. You have very secret, but at least those aggregated amounts, like what is the fraction of people that would go from here, from there, the company would allow us to use. So we use that kind of information to be able to do this kind of splitting of the populations. Okay, so this is one of the things about the compartmental models, is because actually, once you accept that you can have different compartments and many compartmental models to model different populations, you can actually grow the model a lot and introduce many ideas here, okay? So this work here was done together with my colleagues, Luis Gustavo Nonato, Pedro Peixoto. Pedro Peixoto is the guy that had access to that special matrix, the commuting matrix, Thiago Pereira and Claudia Sagastizabal. Okay, very well. And as I said, once you get the grips of it, once you understand it, you can actually do many things with compartmental models. So another control variable that we actually have is the amount of testing we do. Okay, so we added to our model a quarantine state, such that people could go from infected to a quarantine state because they were tested, they got a positive result, okay? And then they move to quarantine, so they stop spreading. Okay, and we can actually control the amount of tests we do. So this was a joint work with the same authors as before, plus Marcelo Cordova and Claudio Struchin, which is the biological guy here, which is the epidemiology of the group. Okay, all the other people are applied mathematicians. Marcelo Cordova is actually an electrical engineer. He was helping us a lot with coding and things like that. We have a lot of applied mathematicians and an epidemiologist. Okay. So we could actually add tests, and Thiago Pereira had already worked with that idea of adding tests to stop a disease like that before COVID. So we had the mathematics that would teach us how testing would affect the number of infected and move them to this quarantine state. So it was relatively easy for us to add that kind of information in our model. Okay, because we had previous knowledge about that. Okay, so in our case, we did not try to model, which would be actually harder to do if we tried to do it properly, active tracing. So basically, we're just doing the test as people demanded it. And the main constraint is the number of tests that we're able to do in a single day in every region. So that was also multi-region in this sense. So the state had a certain amount of tests that they could do in a single day because they have some labs in the state that can actually run the tests. And we were trying to find how many tests we should do in every single region so that would help you to control the spreading of the disease by identifying early people that are infected and moving them early to this quarantine state instead of waiting the whole 10th number of days to go through. Okay, so that was another difference, another thing that we could add. And that was done. But after a while, at the end of the last year, a science miracle occurred and we got a vaccine. And that was amazing. Okay, we got a vaccine in 1 year, actually less than 1 year. So we have now a third control variable, which would be the number of vaccines that you can apply in your population every single day. And now things get a little bit more messy. So but it's not really hard. It's just you have to stay calm and say, okay, now I have 3 types of people. People that are not vaccinated, people that got the first dose, and people that got the 2 doses because the vaccine had 2 doses, okay? And then the number of vaccines that I do, they will move people from one of those SAR models to the other. And you just have to do that in the proper way so that we're able to capture the dynamics. And once you know that people are in this SAR group, which had the first dose, you know that the demand for actual healthcare resources will decrease a little bit, not everything, not all, but at least a little, and it is actually significant. And once they move to the second group here, which is the group that got the second dose, then they would be in a much better shape. So in the sense of sustaining a possible infection and not needing special care from the healthcare system. Okay, and we actually did that in a joint work with some of the authors of the previous paper. Marcelo Cordova did not participate in this one, but all the other ones were here, especially Claudio Struchin, which helped us a lot in designing the proper way to do this modeling here. Okay, this model. So what to do once you have those models? Well, now you can try to write an optimization problem and define some kind of objective that you want to achieve and see what you can do. So what basically we have now, we have something like, we have some state variables, which are the number of people, actually the proportion of people in S, E, I, R, and Q, which is the quarantine state. you have three control variables, which is are not anymore because it's not the basal, the original, the basal reproduction number, but it's actually reproduction number that's changing through time by being modulated by the government. Okay, we have this R variable, little r here. We have the number of tests that you can do every single day in every single region, and you have the number of vaccines that you can apply for each of the doses in every single day. So basically, this is actually two numbers, the number of first doses and the number of second doses that you have to apply. You can think that both of those variables, they are a function of time. And if you start with your ordinary differential equations, once you plug everything into your ordinary differential equation, you get the dynamics of the disease, okay? So how you put that into a computer, you discretize in time. We did that with central differences because it's already good enough for us to get reasonable numerical solution of those equations because, as I said, they are easy, okay? And since we had multiple populations and many periods of times and many compartments and vaccines and all that kind of stuff, we didn't want things to get too big too fast, okay? And then once you do that, the ordinary differential equation, what it basically becomes is a set of linear constraints, linear qualities that couples the new state with the previous states. And once you do this, with the central difference. In the case of central differences, you only have two states to the past that you can need to go from x2. You can get xt plus 1 just knowing xt and xt minus 1. Okay, so you basically do this. Okay, and you can also add some extra constraints here. We'll talk about them later. That they'll try to convey information like you don't want the number of people in I to be so high that the healthcare system would collapse. So you write some constraints on the maximal acceptable number of infectious people in every single moment of time, and things like that. And you also have that, you also can write objectives that try to say how you want the effort to stop the disease to behave. For example, usually our objective, they usually would talk about, basically the main objective will be, we want R to be as big as possible. Because if R is big, what we're saying that people is allowed to go to the streets and life can basically go on in a reasonable and natural way. So people can go around and the economy can thrive, the economy can work. Okay. So in order to do that, we needed to write a very special constraint, which was the number of intensive care units that you needed to cope with the number of sick people. Okay. So the main objective here, the main constraint, which is actually more important than the objective, is to prevent the collapse of the healthcare system. And to do that, we're talking about collapse here if the capacity of ICU units is lower than the demand for the ICU units. So you have more people needing intensive care units than you have units to take care of them, okay? We know the capacity. We can actually grow the capacity slowly, but we can actually grow it. So this would also be another control variable if you want. We didn't work with it as a control variable, but it was actually during the time it would change, but for a short period of time, we would not be able to change it. And basically then what you want to write is something that looks like this. If you define this rho of T as the proportion of the infected that actually demand intensive care unit at time T, you have to add up the number infected in a time window, which is basically the mean time that people would stay in an intensive care unit, and it multiply it by rho of T, that would give how many people demand in that time frame units of the intensive care units, and that should be smaller than the capacity. So that's the basic constraint that you have here. So to make things a little bit more interesting and more realistic, we decided to accept that at least in one point in our model, we would have uncertainty. And that point was chosen to be this demand, because this was something that we would see fluctuating a lot a long time. And what we're going to do, we're going to write something like a probabilistic constraint that say that the capacity is good enough to meet demand with a certain probability. Okay, let's talk how we did it. So what we have basically the time series of the number of cases and the demand on intensive care units. We can compute the ratio between those two things in the time window, as I said before. And by looking at this ratio, we see a time series that we want to model. We decided to use an autoregressive model to do that, where you have this random noise would capture the randomness of this time series. And we're assuming that the random noise is normal with zero mean and a sigma square variance, okay? And what we did, we need to somehow estimate the parameters that conveys the model, okay? So we look at the historical data, we estimate those parameters, and then we use this model to predict the ranges where this whole of t would be in the next couple of weeks or months, okay? So we start from this is the deterministic constraint. We have now a model for the randomness. So we could write down an average constraint, like that in average, we would have this demand accepted. But if you look at the dynamics of that time series, it changes a lot. So it's really not it's too risky to accept only an average constraint like that. So instead of using an average constraint, I'm sorry. Okay, we use what we call a chance constraint, which is say that we will attain capacity up to a certain probability, which is given by the decision maker. Like in 90% of the cases, the capacity will be enough to sustain the demand, okay? And since this is going to run many times in time, if we see that we're going to a bad realization, we can actually increase this constraint here. So this is the average of what would happen, but this here, the red dot, is the 95th percentile that we use it to cope with the demand. And once we did that, what we did, we wrote a code that would solve the control problem, the discretized control problem. And in order to do that, we identify the control variables, we identify the operational constraints. We have other constraints like the number of tests that it can do every single day, and at every single region, the number of IC units you have in every region. If the IC units, they can be shared between the regions, or if they cannot be shared between the regions and things like that. We modeled the problem using JUMP, which is optimization modeling language in Julia, and we used that model to solve the problem by the solver IPOpt. During the modeling, we had to do many little tricks so that we could actually solve the problem, because the problem would get quite big at the end, okay? And we also used the same model to get the initial conditions for the ODE by doing some kind of least square fitting of the previous data with a total variation regularization on the variations in the reproduction number. So what we did that, we developed the model, and for each model, we made some case studies. So the case studies will do things like, for example, in that situation, where you have multiple regions. So what we wanted to see if it was possible to, this would be what we would need to do to cope with the pandemic, with the regional strains of the virus, okay? That we ran the beginning of the last year, like in May of last year, something like that. It was already saying that we would go through 2021 before getting even a little bit close to the herd immunity that people talk about. But then we decided to ask the question, can we do the same? Can we achieve the same control, but allowing the regions to open and close in different times of periods so that people can remain in a strict lockdown for some time, and then they would get some slack and they could go out and work and do their things, and then they would have to go back to this lockdown because we didn't have vaccines yet and things like that. Until we get to the vaccines, can we alternate in time, and can we alternate also in space, so that while some regions are closed, other regions are actually open? Okay, so this color codes here is basically red, we're in a lockdown, white, you're basically living your life free, and then you change from one to the other. And the objective here was to show that we could actually create lockdown schedules that would allow different regions of the state to remain open and working, so that they could produce something and that thing could be used in the other region and things like that. Okay, we also were able to identify that, for example, certain ideas like each region should take care of their own sick people would not work, at least for some specific regions. For example, close to São Paulo capital, you have smaller regions that are very interconnected with the main city. So it doesn't really make sense to consider that the number of IC units are not shared in a pool in this region. So we did some kind of analysis showing that if you share the IC units in a pool, you have a better pattern than we would have for both of the cities. The city that is actually giving IC units to the smaller city, and for the smaller city itself. We also show that we can actually use smart testing. This first results here, they are submitted to be published. They are not accepted yet, so let's wait. But we also wrote a paper showing how to choose the number of testing in different regions so that you could better control the spreading of the disease. And this was actually published in this October, in a very few time ago, in PLOS One. Okay, and we also used our model that talks about 2 doses vaccines to try to answer an important question, at least in Brazil, I believe in the whole world, which was under what condition is it a sensible decision to postpone the second dose. Okay, so we were actually able to run our model and show that under certain conditions it was a good idea to postpone the second dose, and under different conditions it's not a good idea to postpone the second dose, and what are the numbers behind it. So it's not like a feeling or something like that. You have an actual simulation that is based on reasonable numbers that tells you what to do, and that can help you to take a more informed decision. And we also wanted to make sure that what group we should vaccinate first, because some people would say that, oh, maybe it's better for you to vaccinate younger people before because they move more around and they spread more disease. And what we showed here is that depending on the efficacy of the second dose with respect to the first dose, you can postpone or not the second dose. And it's very hard for me to explain to you these images in very short time, but what it's basically saying is that you actually needed a very high efficacy of the first dose to make that decision, to decide that you should postpone the first dose, the second dose, to apply the first dose as much as you can, and then only after a while apply the second dose. And that was actually true for the regional alpha variation, alpha version of the COVID-19 virus of SARS-CoV-2. Okay. I'm finishing.
Oh, okay.
Okay. Okay. I spent 31 minutes. Okay. And okay. But for delta, it's not true because the efficacy of the first dose would decrease. Okay. And that was published at the Public National Academy of Science Journal. Okay, we actually were able to show how many ICU units would be spared if you did the postponement of the second dose in the right amount. Okay, so here are the resources, the articles and the preprints. We have code for that. Everything is in open source and can be used everywhere. Thank you.
Thank you. Can you hear me?
Yes, it's not perfect, but I can hear you.
Ah, okay. Yeah. So, are there questions?
So in your model, have you considered vaccine efficacy?
Yes. In our model, vaccine efficacy is an input number. So, for example, to decide that it was a good idea to postpone the second dose, that was actually a good idea, and we did it in Brazil. We used the fact that the first dose efficacy and the second dose efficacy of the AstraZeneca vaccine, which was one of the main vaccines in the beginning in Brazil, they were quite close to each other. And so in that sense, we could actually estimate the amount of ICU units that would be spared by doing that postponement for 3 months, which was what we did in Brazil.
Other questions? Online? Let me just check if there are online questions.
Oh, there is one. Can you comment about discretize and optimize, over optimize and discretize? Do you see any gain? I will be very sincere right now. I'm an optimization guy, I'm not a control guy. So for me, it was basically discretize and optimize, because then I would go to optimization and do my stuff. Okay. I didn't want to, we didn't even try to do the optimized analysis of the model and things like that. We actually did something like that to show that the model was well-defined and the control problem was actually well-defined, and you can show that would have a unique solution, or at least a solution under certain circumstances, because we chose the modeling functions in the right way. This is written in the first paper, but it's not really what we wanted to do, because we wanted to go to a practical application as fast as we could, because it was very time sensitive, this research here. So we opted for discretize and optimize because it was faster for us, at least, to go.
Any other questions? So I have one quick question. How many parameters did the model finally have? The full model with the vaccination and all the regions and all that. How many parameters did you have to choose or fit before starting the optimization process?
Sorry, I did not understand. How many what?
How many parameters?
How many parameters? The number of parameters is low, because the parameters are basically the maximum are not the Basel reproduction number and the mean times, but the number of variables is quite high. So we had like something like 250,000 variables in our model and 300,000 constraints to solve. So we had to do some tricks to get it to be solved in a reasonable amount of time.
Oh, there is one more question in the chat. Just hold on.
Oh, yes. Is any study on the influence of electromagnetic waves? I don't have an idea, and I don't believe that that would be something important in this case. It doesn't sound like a sensible biological assumption. I never heard of it. So the mutation basically occurs because the virus goes inside you, and viruses they usually multiply very easily, especially RNA virus, which is the case of SARS-CoV-2. So the mutation will just happen very easily while they reproduce inside your body.
Other questions? I guess one quick question. Why robot dance?
Why robot dance? That's a good question. There was a paper, it was not a paper, it was an article, like a news article, called the Hammer and the Dance, just in the beginning of the COVID-19, where the guy would say that what we had to do was something like to do a very severe lockdown, which we call it the Hammer. And after that, we will need to try to create a dance between less strict lockdowns and more free time. And this dance would be something that should be done in a very smart way, okay? So we use a robot dance because what we were actually doing was designing how to do the dance. And it was actually coordinating the dance between different regions. It was an actual dance in some sense. And well, I grew up in the 80s and break dance was very important. So, and robot dance was an important move in break dance. So it's getting to the Olympics right now, actually. So it was also some kind of funny words with my young ages.
Yeah, okay, great. If there are no other questions, let's thank Paulo again. Thanks a lot.
Thank you. Thank you very much for the opportunity.